For what values of x is the rate of change decreasing for the function shown below? First off, this is saying rate of change decreasing, not function decreasing. When your rate of change is decreasing, that implies concave down. So it looks like it probably starts out at concave down right way over here at -4, or maybe negative infinity. It all depends. And it stops its concave down at 0. So we will say, let's assume that this is going on forever, just for example's sake. Let's say negative infinity to 0. And that appears to be it. In their first season, a basketball team practices for 45 minutes per day and makes 199 free throws. The next season, they practice 55 minutes per day and they make 240 free throws, which is true about the rate of change from the first to the second season. So let's actually find the rate of change. Here's the formula for rate of change: f of b minus f of a over b minus a. Now, in this case, a could be 45, which means when I plug in, quote unquote, 45, I get out f of a, which is 199. So b would be 55, and when I plug in b, I get 240, which is f of b. I know you can barely see that, but you get the idea. So f of b is 240 minus f of a, which is 199, over 55, which is b, minus 45. So what, 241 over 10 rounds out nicely to 4.1 or 4 if we're rounding. So let's figure out what we're supposed to do. The rate of change is negative. No. The rate of change is positive since the free throws were all positive numbers in both seasons. Well, free throws are always going to be positive, so that's not why it's positive. You're not going to have negative free throws. It's ridiculous. The rate of change is constant since the practice time and the number of free throws is both increased. That's not necessarily true. The rate of change is positive since the practice time and the number of free throws both increased. That's my guy. So even though some of these has some truths to it, it's not completely true like D is. And even though I didn't have to do that much, I did it anyway, and it was fun. So much fun. Section 1.2, rate of change. Which of the functions shown in the table below could be quadratic? So before I even get into this, I'm going to have to zoom up because these pictures aren't that great. Okay, if I were to take a table and find out all of these numbers are the same, that would be linear. If they're not the same, then step number 2 is do it again. If all of these numbers are the same, that would be quadratic. That's what I'm looking for. I'm going to go to each table. I'm going to zoom in. I'm going to go to each table and see if the rate of change is the same. And if that's the case, then that's the one I want. So let's take a look at A. Okay, in each case, I add 2. Now, these guys are going up by 2. These guys are going up by 2 each and every time. So this guy right here is actually linear because the rate of change is constant over consecutive equal length input value intervals. I nailed that phrase right there. Now let's try this guy. You go down by 3, down by 3, down by 3, down by 3, down by 3. You too, my friend, are linear. Okay, so not you. Let's zoom up. Let's zoom up. Let's try you. I'm going to subtract 1, subtract 2, subtract 3, subtract 4, subtract 5. You are not linear because these numbers are not the same. So let's see if the rate of change is the same. You go down by 1, you go down by 1, you go down by 1, you go down by 1. So this guy is my guy. That's my quadratic equation because the rate of change of the rates of change over consecutive equal length input value intervals are exactly the same. Wow. Zoom out. Circle. Good job, everybody. Okay, let's look at this random problem from AP Precalculus section 1.4. A polynomial function increases from negative infinity to 1, that's an interval, and decreases from 1 to infinity. Which of the following must occur? So this is not that bad of a problem at all. So if I had a coordinate plane, right, I'm just going to draw this out because this problem won't take much longer. At 1, I have some polynomial. All I know, I don't know what it looks like, but all I know is it's increasing. And then once it hits 1, it starts decreasing. And I don't know what it looks like, and I'm purposely making it look bad. So it's asking what must happen between 0 and 2. So here's 0, and here's 2. What must happen is I'm going to have a maximum. So what must happen? I mean, I am going to have a y-intercept. Actually, no, I guess I don't have to have a y-intercept. Technically, I could start this way down here, so I don't need to have a y-intercept. I don't need an x-intercept. Even the picture that I drew doesn't have one. It's not going to have a local minimum, but what it must have is a local maximum. Basically, there's a rule that says if you go from increasing to decreasing, right, you're going to have a local maximum no matter what. I drew it out just to drive home the point. It's a point, get it? Like and subscribe. A of x is x times x minus 8, ooh, cubed, and x plus 3, ooh, to the fourth. We have multiplicity going on here. Now, my multiplicity here is 1, no big deal. My multiplicity here is 3, but most importantly, odd. I'll explain what that means in a second. My multiplicity here is 4, but most importantly, my multiplicity is even. I'll explain that in a second. There's an n there. Now, my degree is found by doing x times 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 x. Why all these x's? Well, if I were to rip all of these apart and write all this out, x times x minus 8 times x minus 8 times x minus 8 times x plus 3 4 times, I would end up foiling out and getting 1, 2, 3, 4, 5, 6, 7, 8 x's. And it's a positive 8 x's. Because you're positive, you're positive, you're positive. And so the degree of this guy is going to be x to the 8th. Why is that important? Because when I graph that, it's going to start like this, and it's going to end like that. Okay, what's going on in between is found by doing this. What I need to do next is I need to find my zeros. So again, I have x, x minus 8 cubed, and x plus 3 to the fourth. My zeros are 0, positive 8, and negative 3. So let's draw ourselves a sign graph. Magic happens at negative 3, at 0, and at 8. Now, I know the beginning of my graph starts up here. Now, when you're dealing with multiplicity, the first 0 I'm heading towards is negative 3. If your multiplicity is even, your graph does not go through the x-axis. It just shoots right off. Then it peaks out. My multiplicity here is 1, which means it goes through 0. Now I'm going to come back up towards 8. My multiplicity for 8 was odd, so it's going to go through and end like that. Okay, so again, when your multiplicity is odd, like here and here, your line goes through that 0. When it's even like it was for negative 3, it bounces off. I care when a of x is positive and also equal to 0, which means where it's above the x-axis. Okay, now it's above the x-axis from negative infinity all the way to negative 3. Now here's the thing. It hits 0 at negative 3. Am I allowed to include 0? Yes, I am. So my first interval is going to be from negative infinity. It hits 0 at negative 3, so still good, still stays positive, and at 0, it hits 0 and includes 0, so I'm going to include 0. Is that my only spot that it's going to stay positive? Well, right now it's negative, but here it hits 0 again, and then stays positive from 8 and on forever. So we're going to hit union. We're going to include 8 because 8 is allowed to be 0, and we're going to go on forever. So there's my guide. Okay, sign graphs involving multiplicity. So much fun. Describe the end behavior in limit notation. Well, what I have here is an x to the third is my largest term here, and I have nothing in front of x to the third, which means I have a regular old cubic. Since my leading coefficient is an invisible positive 1, it's going to look something like this. I don't know exactly how it looks, but all I care about is the fact that I have end behavior. And on the left side, as I move to the left, I go down, and as I move to the right, I go up. So how do I write that out? Well, limit as I move to the left is going to be written out as the limit as x approaches negative infinity because x is heading to the left. Cupid shuffle. Now, as I move to the left, I'm also going down. So the limit as x approaches negative infinity of f of x is going down, which means I'm heading down towards negative infinity. As I move to the right, I'm going up. So the limit as x approaches positive infinity, which means x is getting larger, of f of x is going up towards positive infinity. So since I had an odd degree, it ends and starts out different directions. And since in this case, it's a positive leading coefficient, I start from the bottom, just like Drake, and then I end up top, just like me. All right, we have ourselves a nice little rational function, g of x, and we're being asked 6 questions about it. So first things first, the domain. The way you find the domain of a rational function is you figure out the numbers that make the denominator equal to 0. So in order to do this, what I have to do is I'm going to rewrite this guy. The numerator I really don't have to rewrite because the numerator isn't important for the domain, but I'm going to write it out anyway because I started it. And I had to factor out the denominator. X squared minus 9 is difference of squares. That factors out to x plus 3 and x minus 3. Now, the two numbers that make the denominator equal to 0 would be negative 3 and 3, which means I'm allowed to plug in any number I want except for negative 3 and positive 3. So that gives me a domain of everything negative infinity up to negative 3. I'm not allowed to plug in negative 3, so I'm going to union it and make it negative 3 again because you're not allowed to include negative 3. Negative 3 to 3, union 3 to infinity. Okay? That's the domain. Now to find the y-intercept, I'm going to focus on when x is equal to 0. That's kind of a long way of doing it. So what I can do is I can FOIL out the top but only focus on certain things. Now I know what I can do. I know what's going to happen. All right. And I'm going to be a little lazy here. Since I'm answering questions about the limit, I'm going to kill 2 birds with 1 stone. I'm going to leave the denominator the way it was originally, and I'm going to find the leading coefficient and the last constant of what's completely up here in the numerator. So part number 1, the way you find the leading coefficient is you multiply the leading term in every factor. 4 times x is 4x squared. I don't care about what's in between. Don't care. The way you find the constant is you multiply every constant in every factor. So that's 4 times 5 times negative 2. 4 times 5 is 20. 20 times negative 2 is negative 40. So the y-intercept is going to be the constant divided by the constant. Negative 40 divided by negative 9 is just going to be 40 over 9. Now, the limit as x approaches negative infinity is found by dealing with only the leading coefficients. Now, my leading coefficient is 4x squared over regular x squared. So a little shortcut is I can view the leading terms, not coefficients, but the leading terms as 4 over invisible 1, or just 4. So when I plug in negative infinity in air quotes, when I plug in negative infinity, I get 4. And when I plug in regular infinity, I also get 4. Which means as x increases without bound, the g of x approaches 4. Remember, my end behavior gives me a y or a horizontal asymptote. And that horizontal asymptote is going to be at 4. As x increases without bound is just fancy talk for saying as x approaches infinity. So g of x is going to approach 4. Similarly, as x decreases without bound, the same exact thing is going to happen, and g of x approaches 4 once again. Okay, so 6 questions based off of this rational right here. Fun stuff. All right, we have ourselves some weird looking sine graph here, and we have a couple questions based off of it. So let's attempt to draw this out to the best of my ability. I am absolutely terrible at drawing these out, so I'll do the best I can. Magic happens at -3. Magic happens at 2, and then it's undefined at 0. It goes through 0 at -3. It goes through 0 at 2. It goes from positive to negative. So, I don't know, something like this. I'm so bad at drawing these. Something happens down here. Okay. And then it shows back up. It's undefined, which could mean one of two things. And then it reappears at its negative state, goes through 2, and remains positive all the way until infinity. Now, here's where we have to be careful. I have one of two options that could make something undefined. Option 1 means that this could be a vertical asymptote, or it could be a hole. The thing is, I don't know. But this is the picture that I have. Okay, this is the picture that I have. The graph of f has a maximum at -3 and a minimum at 2. No, that doesn't make sense. The graph of f has a minimum at -3 and a maximum at 2. No, that doesn't make sense. F has 2 distinct real zeros, exactly 2 of them, -3 and 2. Those appear to be the only zeros. So that checks out, but I'm always paranoid and need to double check. F has exactly 3 distinct real zeros. No. The graph of f has a vertical asymptote at x equals 0. Again, here's the thing. That could be true, but I don't know because it could be a hole, and a hole is something that is undefined. So I can't prove that E is true. What I can prove is C is true because there's only 2 places where my line hits a 0, here and here. Because of the infinities, it's not going to come back down and hit a 0 anytime soon. C's got to be my answer because E can't be proven. Possible? Yes. Can it be proven? No. Let's go with C. Ooh, time to show off my ability to sketch a graph, which is bad. I'm given all of this information right here, so I'm just going to draw stuff on this picture and see what happens. At -4, I get 0. At -4, I get 0, so I'm going to put that there. Part A is done. At 6, I get 0, so I'm going to put a dot there. At 6, there I'm done. As I approach -3 from the left side, I hit -infinity. Okay, so what that means is I have a vertical asymptote at -3. So let me try to draw the dashed line that represents the vertical asymptote. And as I go towards -3 from the left, I'm going down. So what's probably going to happen is I'm going to go up here, go through that purple dot, and come down here. But I'm not going to draw yet. I'll kind of wait until the end in case maybe it tells me where things level out or something like that. What else? At -3 coming from the right, I go to positive infinity, so that happens. Okay, so I'm going to have some type of vertical asymptote that as I travel from the left, I go down and then hits the vertical asymptote, reappears up here, and something else happens. So check, 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 check. At regular 4, from the left side, I hit infinity. So that means I have another asymptote. So at regular 4, I have an asymptote again. And from the left side, I'm going towards infinity. So that's going to happen. From the right side of regular 4, I go down to -infinity, so that's going to happen. So probably what's going to happen here is I'm going to come somewhere up here, hit that purple dot, and go down there. But again, I'm not there yet. I'm too scared. As x approaches negative infinity, I go to 2. And as x approaches positive infinity, I go to 2. That's my horizontal asymptote. So I have a horizontal asymptote happening at 2. Oh yeah, also, by the way, forgot to tell you, I don't know why they waited for this at the very end. At 0, I hit 5, which means at 0, I hit 5 there. So now I have everything that I need. Okay, I have everything that I need. I know that in this chunk right here, I level out at regular 2, hit the purple dot, and then go down there at -3. So level out at 2, hit the purple dot, and then, oh gosh, I knew that was going to happen. Although that doesn't look half bad if I just scooch this over just a teensy. No, just a teensy. Let me try it again. Let me just try it again. Let me just try it again. Let me try it again. All right. I'm not going to edit this out. I'm going to keep it. The more time that I have on these videos, the more money I make. Boom. All right. Now I reappear up here, hit that dot, and then go back up there. So reappear up here, hit that dot, something like that happens. Then I reappear down here, go through that purple dot, and level out at 2. So down here, go through that purple dot, level out at 2. And that's my sketch. I'll give myself a pat on the back. That's not too bad. Not too good, but not too bad. But there you go, sketching a graph when given all this information. Hope this helps. Function f is given by f of x equals x squared minus 9 over x squared plus 8x plus 15. Which of the following describes the function f? They care about holes. Holes exist when you have a parentheses and you have the exact same amount of parentheses up here that you have down there when these two guys are exactly the same. So what I need to do is I need to factor the numerator and I need to factor the denominator and see if I have something up here that's exactly the same as something down there. If I do, hole. Now I have x squared minus 9, that's a difference of squares, so two numbers that multiply out to -9 that are the same digit are going to be x plus 3 and x minus 3. Two numbers that add up to 8 and multiply out to 15 are going to be x positive 3 and x positive 5. Now what I care about are the numbers that make each factor equal to 0. -3 would make u equal to 0. Regular 3 would make u equal to 0. -3 would make u equal to 0. -5 would make u equal to 0. I only care about one thing here, and that is the hole. Again, the hole exists when I have a parentheses up here that's the exact same as the parentheses down here, and no more repeats anywhere else. That happens right here. So my factor is x plus 3, but the magic number where that happens at is at x equals -3. So there is a hole at x equals -3. And that's my guy, baby. Write the equation for the slant asymptote for the following function. In order for you to know that you have a slant asymptote, one thing needs to happen. The degree in the numerator has to be 1 higher than the degree in the denominator. Does that happen here? Yes, it does. Now, the way we set this up is we do polynomial long division. It's important for you to understand that if we're going to do polynomial long division, everything has to be in order, and anything in between or at the end that's missing has to be filled in with zeros. What do I mean? Well, the numerator is always the guy that goes into the division symbol. So I'm going to go 9x to the 4th. I'm missing an x cubed here. So I have to replace that with 0x cubed. And then I keep going in order. Minus 5x squared plus 3x minus 6. Make sure it's in descending order, and if it's not, change it that way. Now this guy is going to be the factor that's being divided from it, so I'm going to write that over here, and even though it might not be necessary, I always like to add those extra things at the end that aren't there. Like I'm missing an x and I'm missing a regular value, so I'll add 0x and I'll add 0. Is it necessary? I don't know, but I do it anyway. This is how you do polynomial long division. 3x cubed times what gets me 9x to the 4th? Well, 3 times 3 is 9, and x cubed times x is x to the 4th. Take that number and multiply it to the entire factor. 3 times 3x squared is cubed is 9x to the fourth. This will always be the same unless you did something wrong. 3 times x, or 3x times negative 4x squared is going to be negative 12x cubed plus 0x, because 3 times 0, plus 0x. That should be squared. My bad. Now you subtract this entire row, which means you flip the signs of everything in here. This will disappear. This will become regular 12x to the third, drop down the minus 5x squared, drop down the 3x. Now this last part, oh, and always drop down the negative 6, even though it's not that important. Now, why did I just whisper that? How dare I say it's not that important? Because my next step is to repeat what I did at the very beginning. 3x cubed times what gets me 12x cubed? Well, 3 times 4 is 12. And x cubed times 1 is x cubed, so I don't need anything more. Now, at this stage, I'm done. And if you might be thinking, well, you have to multiply 4 to that and find your remainder. No, I don't. I don't care about the remainder when it comes to my slant asymptote. Once I get a linear equation in slope-intercept form, I have my slant asymptote, and the equation for my slant asymptote is 3x plus 4, y equals 3x plus 4, and that is a line in slope-intercept form. So that's it. I'm done. The function g is defined by f such that g of x equals 3 times f of 2x minus b. If f of 2 is a, f of 4 is 8, g of 1 is 7, and g of 2 is 19, what is the value of a? Holy crap. Well, let's see what I can do. Okay, let's see what I can do. I'm given g of x equals stuff, and I'm told that f of 2 equals stuff, and f of 4 equals stuff, and g of whatever. Let's find the things that I can find. Let's find out what g of 1 is. Okay, g of x is that guy right there. So g of 1 is going to be 3 times f of 2, replace x with 1, minus b. So this simplifies to 3 times f of 2 minus b. Ooh, f of 2 is a. So this becomes 3a minus b. Now, does that get me anywhere? No, it's asking for the value of a, and, I have to do a little bit more because there's no b here, so I'm not quite done yet. So I found g of 1. Let's find g of 2. G of 2 is going to be 3 times f of 2 times, replace x with 2, minus b. That becomes 3 times f of 4 minus b. Oh, look, f of 4 is 8. So 3 times 8 minus b is going to be 3 times 8, which is 24, minus b. Now, this is what else we know, because right now I'm not really getting anywhere, but here's what else I know. I know that g of 2 is also 19. I also know that g of 1 is 7. So what I can do is I could solve both of these equations and see what I come up with. Well, first off, let me do this, because now what I have is I have a system of equations where I have 7 equals 3a minus b, and I have 19 equals 24 minus b. I can find b right here in this equation right here. So if I take this bottom equation and subtract 24 from it, I get negative 5 equals negative b. If negative 5 is negative b, then positive 5 is positive b, so b becomes 5. I could take that guy right there and the top equation and replace b with 5. 7 equals 3a minus 5 has me adding 5 to both sides to get 12 equals 3a. Divide both sides by 3, and after all of that, a is 4. So a pretty gross problem, not a fun problem at all. Again, I stole this from the internet, so I don't know. It is what it is. Hopefully you never see a problem like it, but we did it anyway just in case. A rectangle is inscribed a circle with a diameter of 12. Here's my rectangle living inside, touching the outside of the circle. Diameter right there is 12. It gives us a width of x. Tells us the other width is the square root of 144 minus x squared. They get that from the Pythagorean theorem just for fun. The function a of x is that guy, x times the square root of 144 minus x squared. So again, that comes from, that times that area formula, and that models the area of the rectangle. Great. What is the restricted domain of the function? This is asking us what values am I allowed to plug in? Well, first things first, we're looking at this rectangle right here, and this rectangle is going to tell us what we're allowed to plug in. Now, if we're going to represent x as a side, you are absolutely not allowed to plug in any negatives because you can't have a negative side, so negatives don't count. I also can't have a side that is 0. But I could have a side that's 0.1. It would be a very skinny rectangle, but I could have a side that is 0.1. So basically, as long as it's greater than 0, I'm allowed to plug it in. Now, what's the largest value I'm going to plug in? Well, as we see this square root right here, that tells us right there that if I have 144 minus something, that at some point there's a possibility that I end up with a negative square root, and you can't have negative square roots. So what number would make this square root equal to 0? 12. Because 12 squared is 144, and 144 minus 144 is 0. So does that mean 12, put a little bracket there, is going to be the absolute largest number that I can plug in? No. I'm not allowed to plug in 12. I'm allowed to plug in 11.99999, but if I plug in 12, then all of a sudden I'm saying I have a right triangle with a hypotenuse of 12 and a leg of 12, and geometry says that's against the law. So my restricted domain is everything from 0 to 12, not including 0, not including 12. Yippee. Part 2 is asking us what's the restricted range of the function. In other words, what is the largest and smallest possible values that I can get when I plug in 0 or something close to 0 and 12 or something close to 12. So I'm going to run to my calculator. I'm going to plug numbers in that are awfully close to 0 and plug numbers in that are awfully close to 12 and see what I end up getting. All right, so let's go to our calculator and type out this function. We've got x times the square root of 144 minus x squared. Now, what we know is our domain is everything from 1 to 12. So from 0 to 12, not including. So let's actually change our window and make it like -1 to 13 so we can see what we need to see. Okay? Boom, graph. Now it shoots way up here, so maybe let's maximize the window to, 100 and see if that seems to be good enough. Hit graph again, and that does seem to be good enough. Oh, how nice. Now notice how it cuts off at 12. That's because we already know we're not allowed to plug in 12 or anything after that. Now, why doesn't it cut off there? Well, because our calculator doesn't realize we're doing a real life problem. So, it doesn't realize we're doing like negative x stuff. Okay? Now, what I need to do is I need to find my range. Without plugging or typing anything in, I know that my range is going to be from 0, but not including 0, to 199. So my smallest value, I already know what's going to happen. It's going to go through 0. My smallest value is 0.000001. So my smallest range, if I have like the skinniest triangle, is going to be 0, just not including 0. So I'll make sure I write that down. Now, in order to find what my maximum range is, I have to go find my maximum. So I'm going to do second calc. I'm going to set a range for the maximum, and it looks like it's going to happen between, basically, I'm at 6, so I might as well hit enter for that. And as long as I go to the right of the bump there, hit enter on that, my maximum is going to live somewhere in between. And my maximum happens when x equals 8.4, blah, 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 blah. But that maximum value is 72. So my range is going to be between 0 and 72. So let's go back and write that out. All right, so what I got was basically 0.000001. So I'll say 0, but not exactly 0. And pretty much 72, but not 72. It's got to be smaller than 72. So my smallest area is going to be like 0.00000, and my largest possible area is going to be like, 79.99 or 71.9999999. What is the maximum area of the rectangle? Well, let's go back to our calculator, type that in, and see what the maximum area is. Hey, what's the maximum value? 72, stupid. Go back. Well, I didn't really need to do that because I did that in part B. So 72. I don't know why I did that. Dummy me. But, anyway, thanks for watching. This is a piecewise function. It's a calculator example, but I'm not going to use my calculator because the numbers seem to be friendly enough. The piecewise example says we're going to use this quadratic equation right here when x is in between -2 and 3. We're going to use this linear equation right here when x is in between 3, not including, and 10, not including. And the answer is going to be 5 if the x value is in between 10 and 12. So when f is 1, that applies to this scenario right here. So when f is 1 equals 9 times 1 minus 1 squared. 9 times 1 is 9. 1 squared is 1. The answer is 8. Easy peasy. When f is 10, that includes that guy right there. And when f is 10, no matter what, you're going to get 5. So f of 10 is 5. Hope this helps. A local community has a new text alert system that residents can sign up for. The table gives values of P of T in the number of residents for selected values of T in weeks since the community started the system. If a sequence is constructed to represent these data, because it's plural, which of the following best applies to the situation? So it looks like what I'm doing is I am definitely exponential. Am I multiplying 1.5? Yeah, I am multiplying. Well, 40 times 1.5 is 60. 60 times 1.5. So I'm multiplying 1.5. We're going to use, they want us to use what looks like to be a geometric sequence, so I'll set that up. A sub n equals a sub 1, the first term, times r to the n minus 1. Okay. Why they're using n and not t, I'm not sure, but not my problem. Let me see. I determined that the common ratio is 1.5, but they want us to write it out as 3/2. The first day is actually 60. So a sub n equals 60 times 3/2 to the n minus 1. Which is neither of those. So it's definitely not u and it's definitely not u. So my job is to now figure out, all right, well, which one of these is that? Well, if I were to look at it like this, all right, if I were to multiply, or better yet, rip this out and say, look, I don't like the n minus 1. Let's get rid of the n minus 1. Let's get rid of the n minus 1 by ripping those apart. So I can make it 60 times 3/2 n times 3/2, and if you're to the -1, and if you're wondering what did he do, what he did is originally if you have two terms of the same base being multiplied together, you add the exponent. So going in reverse, I did that. Now what I can do is I can say I have a fraction to the -1 power. Flip that. 60 times 3/2 to the nth. Flip that, making it 2/3. 2/3 of 60 is 40. So a sub n equals 40 times 3 over 2 to the n. Now, maybe I did too much. And some of you might be like, well, didn't we also learn, sir, didn't we also learn that an exponential function looks like this? Y equals a times b to the x. B is your common ratio, so you already knew it was 3 over 2, which automatically eliminates you because you're 2 over 3. So that's that. And isn't a what this whole thing would be if x is 0, so 40? Couldn't you have just done it that way? Yeah, we could. But when I saw the a sub n's, I just was like, oh, well, maybe they want arithmetic or geometric sequence stuff, and I went with it. I was wrong. It worked out in the end. But now you have two ways of doing the same exact problem. So you're welcome. Like and subscribe. The graph above represents the amount of caffeine in an adult's blood after they drink 1 cup of coffee, where X is the hours since consuming the coffee and Y is the amount of caffeine in milligrams. So hours, milligrams, great. Which of the following equations defines the function in the graph? So without doing too much, what it appears I have is at 0, I have 100. Okay, so the first things first, if you're looking at an equation like this, okay, which is what I have, all right, that's my initial amount. So A is going to be 100. So Y equals 100. B is, I don't know yet, but what I do have is dk. So dk means B has to be in between 0 and 1, which excludes U and which excludes U. And so it's going to be to the x power. Now, I have to choose between 0.85 and 1.5. So if I were to plug in 1, right, into U, I would get 100 times 0.85 to the first, or 100 times 0.85, which is going to be 85. So let's see what happens when I go to 1. Seems to match up with 85. So, yep, you're my guy. If I were to try C, I would do the same thing and get, let's plug in 1 and 0.15, and that's going to equal 15, which is not what I want. Okay, and this also makes sense because this is saying that we are going to decrease, but not at a huge rate. You know, you're losing 15% per, what is this, hour? So that's what's going on here. This is like you're losing almost everything per hour, and that's going to be a huge dip, which is not what we have. So my guy is going to be A. An exponential function in the form f of x equals a times b to the x has a growth factor of 1.56 and crosses the y-axis at 0.85. On the closed interval 0, 4, what is the maximum value? All right, so let's set up our equation first off. We have something in the form a times b to the x. This is going to be your initial value at the very beginning of everything. In other words, the beginning of everything happens when x is 0. So y equals 0.85, a positive number. The growth factor is 1.56, so that's going to be my b, 1.56 to the x. So what I have is I have something in the form of exponential growth. Now it wants me to, on a closed interval 0, 4, find the maximum value of f. Well, this is going to make sense that if I have 0 to 4, 4 is going to be my maximum. So what I have to do is I just have to throw that in my calculator, plug in 4, and see what value I get. So we're just going to plug in the equation that we came up with. We came up with 0.85 parentheses 1.56, close the parentheses, to the x power. Now we care about what happens between the intervals 0 and 4. So when I hit graph, that's exponential. And so as you move to the right, your value gets bigger because this is exponential growth, because the growth factor is greater than 1. Now, my maximum is going to happen all the way to the right of the rightmost part of the interval. So basically, my maximum happens at 4. So if I go and type out second trace, hit value, hit 4, I'm going to get that number right there, which matches up with the answer C. So basically, you know, you're finding the maximum knowing very well that your maximum is going to be all the way to the right for this one. And when I did that, I get 5.034, so the answer is C. Given that m and n are positive integers, find the value of n plus n if this happens. Gross. All right, so let's move stuff around. I mean, let's do a little bit of function manipulation and see what happens, what we get. So I'm going to write this out as 12. Okay. I'm going to move x to the negative n to the bottom and make it x to the positive n. Whenever you have things being multiplied to an exponent, you multiply exponents. In this case, you would distribute that. So that parentheses down there becomes m to the negative 2 x to the positive 6. I can move u upstairs. So 12 over x to the nth. I can move u upstairs and make u m squared. And what was that? X to the 6th? X to the 6th stays on the bottom. So what I have is 12 m squared over x to the n plus 2. No, I'm sorry, n plus 6. N plus 6. I'm looking at that guy. That's supposed to match up with 108 over x to the 9th. 12 times what is 108? 12 times 3 squared is 108. 12 times 9 is 108. That would make m 3. Because 12 times 3 squared is 12 times 9, which is 108. Great. If I were to replace n with 3, I would get 3 plus 6, which is 9. So what a strange problem this is indeed. But that's not what I want. I'm still not done. I almost circled B and was like, oh, hooray. I'm supposed to find m plus n. M plus n is 3 plus 3, which is 6. Very tricky problem, very difficult, but you know, we did it and it was so much fun. A radioactive element has a half-life of 11 years. In other words, every 11 years it goes by half. If 20 grams of the element is remaining after 25 years, what was the initial mass in grams of the element? So this is what I'm going to do. I'm going to write out the half-life formula that I know how. So this is an exponential formula. Okay, A is always what you start out with. B is going to be your growth factor, and X in this case is going to be time. So do I know what we start out with right away? No, but what I do know is we end with 20. I don't know my initial amount. I do know that I'm taking a half of it every 11 years. So how do I show every 11 years? By doing X over 11. Now, I care about what happens at 25. So I'm going to rewrite this to be 20 equals A times a half to the 25 over 11. So this is how I'm going to handle this problem because now I need a calculator to take over. I'm going to find 1/2 to the 25 over 11, get some number, and 20 divided by that number is going to get me my A. So let's see what happens. So now I'm at the point where I really can't do much without a calculator. So I have two calculations that I need to do. First thing I need to do is I need to figure out what 1/2 to the 25 over 11th power is. So I'm typing that out. If I can just type and not make a little typo, 25 over 11. It's going to give me that number right there. Now I'm going to take 20 and divide that number from 20. So I can divide that number if I want to by hitting second and then that little negative symbol there. And what that does is that uses that whole number so I get more accurate of an answer, which gives me that guy right there. And darned if that isn't awfully close to C, which it is. So that's my answer. So the A I got is 96.6, I think it was 665 or something like that. So that gives me C. Close enough. I mean, you're not looking at exact when we're dealing with some rounding error, but no, that's my guy, and I'm sticking with C. C is the answer. C it is. C. C means yes. A statistician recorded the pregnancy rate of 1,000 U.S. women aged whatever to whatever. A linear regression was used to develop a linear model for the pregnancy rate over time. The figure shows a graph of the residuals of linear regression, which of the following is true. Now, looking at these dots, okay, what you're looking for with a residual model is, do you have a pattern? Okay. In other words, like if I were to give you a residual plot that looks like this, that's a clear quadratic pattern. So when you have a clear pattern, a linear model is not appropriate. So I don't see a pattern. I have a dot down here, 4 dots up here, 5 dots down there, 3 dots up here. I don't have anything quadratic. That's not like, that doesn't look cubic or anything like that. It's not like you're going to be like, oh, well, yeah, I could definitely do that. No, not really. I don't have any pattern. So since I don't have a clear pattern, linear is appropriate. So let's choose that. The linear model is appropriate because the residual plots demonstrate a clear pattern. No, linear is appropriate, but it's because it doesn't present a pattern. The linear model is appropriate because the residual plot does not demonstrate a pattern. Yep. The linear model is not. Nope. The linear model is not. Nope. So what you're looking for with residual plots is, do you have a pattern? No. Then it's linear. Identify all statements that are true. Ugh. All right. F of g of x. Let's find f of g of x. This is going to take us a minute. F of g of x means I take f, and for every, writing it down. For every x that I have, replace it with g. So just take that x and write out g. Okay, I can handle that. G of f is you're going to take g, which is this, and replace every x with f, so they're the same. Oh, how nice. So not you. 2 says g of h. So let's find out what g of h is. G of h means I start out with g and replace the x with an h. So instead of x minus 4, 3x plus 4 minus 4 over 3. These guys cancel out. 3x over 3 is just going to be x. So that's g of h. Let's see what h of g is. H of g means I start out with h, replace every x with g. Don't forget the plus 4. These guys cancel out. And then I'll have x minus 4 plus 4, which is just x. Oh, how nice. Of course, I have to keep going because it's never that simple. H of j has me start out with that. So start out with h, substitute j for every x. This is h of j. So you get 9x minus 12 plus 4 is going to be 9x minus 12 plus 4 is minus 8. Now let's do j of h, which has me start out with j and replaces every x with h. So 9x plus 12 minus 4. Oh, we finally have one. We have one that doesn't match up. So you don't work, friend, and you're going to be my guy. A rocket is launched from ground level and is in flight for 4 seconds. I see it. Its height and feet can be modeled by that equation right there, which is graphed on the figure below. Find an expression H inverse for which the rocket is increasing and determine the domain of its inverse. All right, I got it. In order for you to find the inverse, the first thing I want to do is I want to turn any f of x's, or in this case, h of x's, into y, because that helps me understand the math better. My little ADHD brain can't handle an h of x floating around. So let me rewrite this out. Y equals negative 16 parentheses x minus 2 in parentheses squared plus 64. Second thing that you're going to do is you're going to swap your x and your y values. So y is now x and x is now y. Negative 16, y minus 2 squared plus 64. What you're going to do is you are going to find your new y value. So I'm going to subtract 64 from both sides. So now what that will look like is x minus 64 on the left, I'm kind of being a little lazy here, equals negative 16 times y minus 2 squared. Divide both sides by negative 16. Divide both sides by negative 16. And when you do that, I'm going to be a little clever here. When you divide everything by negative 16, I'm going to actually change this into negative x plus 64 and positive. I'm flipping all the signs because I'm dividing by a negative. I don't think you have to do that, but it looks like I don't see any negative 16s lingering down here, so I'm going to make it positive. So I'm going to make you negative x plus 64 over positive 16. And once again, what I did is by dividing a negative, I can flip-flop everything. That equals y minus 2 in parentheses squared. Now, in order for you to get y all by itself, we need to square root both sides. When you square root both sides, you usually have a positive or a negative, right? But in this case, they only want the positive part. And that is the only part that's going to make sense. So a positive square root when graphed looks like this. A negative square root when graphed looks like this. Obviously, I don't want stuff going underground. I want stuff going above ground. So I am going to get rid of you. And I'm only going to keep the positive part. So I really don't need that sign there anymore. What that does is I now have the big square root of negative x plus 64 over 16 equals, these guys cancel out, y minus 2. Add 2 to both sides. Let's see how they want me to write it. I have square root of negative x plus 64 over 16 plus 2 equals y. Let's flip-flop it and turn that into h inverse equals square root negative x plus 64 over 16 plus 2. Now this is my height. Okay. By doing it this way, I get this picture right here. And of course, that's obviously not drawn to scale because these go by 2s and these go by 10s and stuff like that. So it's not drawn to scale at all. But by doing this, I am now flip-flopping what my y, x, and x-axis stand for. The x-axis now stands for height. When I shoot a rocket up in the air, I really hope it doesn't go 2 feet in the air. I'm expecting it to go 64. So now that my x and my y are swapped, my new domain would be way the heck over here and would be 64. So B is my answer. So a lot to do there. There was a lot there. Not only did we have to find the inverse, we had to make sure it was positive only, and then we had to make sure that we had the right domain. But we did it, and I'm proud of each and every one of you. The pH of a substance can be calculated by the formula above. pH equals negative log no base x, where x represents the concentration of hydrogen atoms of the substance in moles per liter. Nifty. If lemon juice has a pH of 2.27, determine the pH of an acid with 2 times the hydrogen ion concentration as lemon juice. Thank you, Lord, we have one of these guys. So let me do two things. My pH is 2.27, so let me rewrite this equation. Instead of pH, I'm going to do 2.27. That's going to equal negative log. Now, since there's no base, I'm going to write out the fact that we have an invisible base 10 and then of x. What I want to do is I want to write that out in exponential form. So the way you write something down in exponential form is if I give you log base b of y equals x, you can write that out as b to the x equals y. Okay, so I'm going to rewrite, well, first off, let's do this. That negative is bothering me. Let's multiply both sides by negative. Negative 2.27 equals regular log base 10 of x. Using this formula, I can rewrite this out as 10 to the negative 0.27, negative 2.27 equals x. Now, this is how I'm going to finish up this problem. I need to throw that into my calculator and get x equals stuff. Okay. What that does is that gives me the ion concentration of hydrogen atoms and blah, 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 blah. Okay, of that pH. What I want to do is I want to take that. I want to double it and then find the pH of that. So all of my calculator, what you're going to see me do is you're going to see me type this guy out. You're going to then see me multiply it by 2 and then throw it back into this formula up here to get a number. All right, so let's run to the calculator and see what happens when I do that. Well, this is going to be a gross one. You ready? So first thing we need to do is we need to do 10 to the, which is that guy right there, negative 2.27. We need to double that, so times 2. And now that I have that, I'm going to throw it back into that original equation that hopefully you see right there on the right side. So negative log base 10 is negative log. And rather than me typing that whole thing out, a little trick that I could use is I can hit second negative symbol, and it lets me plug in the answer that I just got, hit enter, and I get 1.96 blah, 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 which seems to match up with C. So let me show you what that looks like back on the problem. We'll be done. All right, so in this case, x equals 0.00537 blah, 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 blah. I took that and I multiplied that by 2 to give me 2 times the hydrogen atom concentration. And that gave me the number 0.01074, blah, 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 blah. Okay, so an acid with 2 times that has this, and I need to find the original pH of that. So what I did is I said pH equals, and I typed out negative log regular base 10 of 0.01074, blah, 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 blah. I got 1.96897, blah, 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 which ended up being C. So very unique and challenging problem, pretty difficult stuff. Select values of f of x are shown in this table above. If the f inverse is g of x, which of the following expressions are equivalent to f of x? All right, well, let's do this. Let's make a table for g of x. If g of x is the inverse, we know that all I have to do is just swap them. Swap them. Swap them good. Which of the following expressions are equivalent to 4? So I need to plug in all of these guys and see which one gets 4. So f of g of 4. First off, g of 4 means I'm going to go over here and let me do this. Let me split this up. Let me put this in red over here. F of g of 4 means, let's find out g of 4, which is 2. So f of g of 4 means f of 2, and f of 2 is 4. Check. Let me do this in blue. F of 2 is going to be 4. I already knew that. plus g of 2 is going to be 1. You're 5. I wanted 4. Sorry. F of 2, I kind of know what's going to happen, is 4 minus g of 2 is 1. That's not 4. That's 3. So not you. So the only guy that seems to work is just 1. Oh, inverses. You get me every time. Find all relevant information from the given function, sketch the graph. Now, I have f of x equals ln of x plus 8 in parentheses plus 3. Now, those of you who watch all of my videos, you know very well that if I'm graphing something that is a log, and yes, this is a log because ln is log base e, I'm going to compare it to f of x equals a, which gives me a vertical stretch or compression, times log base b, which is my base, but also deals with a horizontal stretch or dilation, or shrink, or whatever you want to call it, x minus h plus k. H determines left or right movement. K determines up or down movement. You make things look steeper, skinnier, whatever. You move, left to the right. You make things shorter, okay, so to speak. Now, this is very important. I care about if A is positive, and it is. It's invisible 1. And when that happens, you get a graph that looks something like this. Now, a couple things are happening here before I can really answer these questions and feel happy about it. One thing I have is I have a vertical asymptote. Now, vertical asymptote exists at places where you're not allowed to plug in specific numbers. Now, I'm not allowed to plug in anything that would make this parentheses negative or 0. Why? Because you're not allowed to take the ln or a log of a negative number or of a 0 number. So if I were to plug in negative 8, I would have ln of 0. That's not allowed. Anything bigger than negative 8 is okay. Now, it just so happens that h is negative 8 in this case. H is negative 8. My vertical asymptote is found at the equation x equals negative 8. So asymptote is x equals negative 8. Anything smaller than negative 8, not allowed to plug in. Anything bigger than negative 8, I'm gold. Now what that means is I'm not allowed to plug in anything that is negative 8 or smaller than that. So my domain is found by doing essentially h to infinity. That's my domain. So in this case, my domain is going to be negative 8, okay, not including negative 8 because you're not allowed to take the ln of 0, to infinity, to infinity. Here, we'll turn that 0 into double 0. Look at that. Perfect. Nailed it. Now, if you're looking at this and saying, we move this up 3, how does that affect my range? It doesn't. No matter what, this is going to continue going downward, and this is going to continue going up and to the right no matter what. So my range is always going to be, in this case, everything. And as long as A is positive, my range is always going to be infinity, the negative version, to regular infinity. Always, always, always. Now, this is where it gets weird. Okay, my end behavior. Usually when you think end behavior, you think, all right, ln as x approaches x to the negative infinity, but we can't. We're not allowed to go to the negative infinity. The furthest I can go moving to the left is to negative 8. So what I will say is the limit as x approaches negative 8 from the right side. Okay, negative 8. Of course, 8 and infinity are similar looking things, so, that's supposed to look like that. From the right side of f of x. As I move to negative 8, I hit a brick wall. But right before I hit that brick wall, I'm going down to negative infinity, so that's the left side of my end behavior. The right side of my end behavior is I'm allowed to go all the way to the right, and as I keep moving to the right, I also keep moving up. So the limit as x approaches positive infinity of f of x is going to equal infinity. Now let's take that picture and make it look a little bit better. Okay, this is the worst part of all of this. No calculator allowed, no calculator needed. We'll be all right. First thing that happens is I know that I have a horizontal or a vertical asymptote at -8. Now, there's a little rule that says whatever this number is, okay, that is going to be your y value, 1 unit to the right of your vertical asymptote. So if this was 3 and if this was -7, I have a point right there. And that's basically how I'm going to wrap this problem up, because as I move to the right, I am now dealing with a horizontal stretch involving E, and I really can't label stuff without calling things E, and I'm not about to do that. So I'm just going to draw this guy right here. It's going to keep going up and to the right. Okay, not the prettiest picture ever, but we accomplished everything we needed to accomplish. And again, that point right there is -7, -3. Not the prettiest problem ever, but we did it. Approximate log base b of 18, given that log base b of 2 is whatever, and log base b of 3 is whatever. It's a calculator problem. Okay, so let me think what I can do. I can try to think of maybe some kind of like ln reg or logarithmic regression, but I have another idea. Let's pretend that I'm not allowed to use the calculator. Let's just make believe I'm not allowed to use the calculator. What I notice is that all of these guys have the same base, right? So if I wanted to, I can basically rip this apart and say log base b of 18 is pretty much the same as, can I make 18 the same as, wait a minute, 2 times 3 times 3 again is 18. So this is a true statement. 2 times 3 times 3. That's a true statement. Wait a minute. When I multiply stuff inside of a log, I can expand that using addition. In other words, if I were to give you something like log base b of 2 plus log base b of 3, I would get log base b of 2 times 3. So working backwards, I can write this out as log base b of 2 plus log base b of 3 plus log base b of 3. Now, normally we're used to doing something that looks like this and getting to something that looks like this, but now we're working backwards. So is this kind of a weird problem? Like, would everybody know that I'm supposed to turn this into this? No, but that's why we do these problems. Just so happens that we know log base b of 2 is that guy right there, 0.4307, plus log base b of 3 is 0.6827, plus log base b, again, 0.6827. So the only reason why I would need my calculator is to do this calculation right here. But let's just say I can do this in my head. This ends up being 1.7961. So yeah, let's just make believe we used a calculator. And we end up with D. Very unique problem. You have to think outside the box with this one. A logarithmic function g is created by transforming the function f of x equals log base 5 of x such that g of x is 1/2 f of x plus 3 plus 2. Find inverse g of 3. All right, this is going to be a doozy. First things first, it tells us what f of x is. It's that. Then they want us to do half of f of x plus 3 plus 2. So let's do this. Let's find out what f of x plus 3 is. Okay, won't take long. If f of x is log base 5 of x, then f of x plus 3 is log base 5 of x plus 3. NBD, as the kids say, for no big deal. Now, g of x is now going to be 1/2 of f of x plus 3, or log base 5 of x plus 3 plus 2. They want me to find the inverse and then plug in 3. So this is how I find the inverse. I don't like the g of x there, it throws me off, so I'm going to rewrite this as y equals 1/2 log base 5 of x plus 3 plus 2. Step number 1 in finding an inverse is swap your x and y values. So now I have 1/2 log base 5 of y plus 3 plus 2. And now I have to solve for my new y. First thing I'm going to do is I'm going to subtract 2 from both sides. So I have x minus 2 equals 1/2 log base 5 of y plus 3. You're now gone. I have to get rid of that half, so why don't I multiply both sides by 4, by 2 I mean, multiply both sides by 2. That crosses these guys out, and I distribute on the left. So I have, let me write it up here because I'm running out of space, 2x minus 4 equals log base 3 of y plus 3. Now I have to solve for y, and y is inside of a log. That's no good. I have to get rid of that log. How can I get rid of a log base 3? Take 3 to the of both sides. Okay, take 3 to the of both sides, and that gets rid of the 3 in the log base 3. And now I have 3 to the 2x minus 4 equals y plus 3. If I subtract 3 from both sides, I now have 3 to the 2x minus 4 minus 3 equals y. Well, it just so happens that y is now my G inverse. I got y all by itself, so now I can call it G inverse. Great. Gross. Not the end of the world. Because what I have to do now is I have to take the 3 that I'm given here and plug that 3 in. So that is going to be 3 to the 2 times 3 minus 4 minus 3. 2 times 3 is 6. 6 minus 4 is 2. 3 squared minus 3 is 9 minus 3, 6. So after all of that, it's a pretty gross problem, but we did it. The function ln of a of t over a equals kt models the amount of a particular radioactive substance that remains after t hours, where a is the initial amount of the substance, k is the rate of decay. And so a of t would be the total amount when all is said and done. If 24 grams of the substance decay to 8 grams after 36 hours, after approximately how many hours would the initial amount have been reduced to a half? Ugh. All right, so this is going to be gross. This is going to be really gross. 24 is what I start out with. So A is going to be 24. All right. My amount after 36 hours, so T is going to be 36. My total amount is going to be A of T is 8. My job is to find the rate so that when I do find the rate, I can do part 2 here. So I'm kind of doing 2 of these problems in one, which means I'm probably going to have to whip out the calculator twice. NBD, as the kids say, NBD. ln of A of T is going to be ln of 8 over A is 24 equals K times 36. So this is what I'm going to do in my calculator. In my calculator, I'm going to type this guy out. Okay, I'm going to type that guy out right there and get some gross number. Once I get that gross number, I'll have 36 equals K. I'll divide both sides by 36, and then K will equal something brand new. So one more time, I'm going to run to my calculator and find out what ln of 8 over 24 is, get a number, divide that number by 36. That gets me K, which is going to be my rate of decay, something that I'm going to need in order to do part 2 here, right there. Right, ln, there you are, of, what was it, 8 over 24. So let's type that out. It's going to equal a gross number. There it is. Take that number, divide it by 36. And then our k is going to equal negative 0.30517, blah, blah, blah. So we'll actually use all of those numbers until we hit that double zero, just to keep things as accurate as humanly possible. All right, so after doing that, we got a pretty gross number, negative 0.030517. Then it was like 008, but I'm going to stop right there. Now that I know k is that, I can go back to this original equation to answer part 2. Part 2 says, how many hours would the initial amount have been reduced to half? Okay, so ln of, now remember the original amount was 24. I'm no mathematician, but half of that is 12. My job is to find t. I now know what k is, so negative 0.030517 times t is going to help me do that. So very similar to what I did over here. I'm going to type this guy into my calculator. When I type this guy into my calculator, I'm going to get a gross number. Then I'm going to divide that gross number by another gross number, which is this guy right here. And when I divide that gross number by a gross number, I get a gross number which represents how much time it takes for this substance to get cut in half. So let's go away and do that again. All right, so this time I'm going to take ln of 0.5 or a half, however you want to write it out. Right. Hit enter on that guy, and it's going to give me that number, 0. Who cares? Negative 0. Who cares? What I'm going to do is I'm going to divide that number by negative 0.030517, hit enter, and I get something to the tune of 22.713, blah, 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 blah. So let's go back, write down our final answer. We can be done with this terrible problem. All right, so after we did that, we ended up with 22 we rounded it to 713. It was like 7134 or whatever. So 3 decimal places is standard for AP, so we'll go with that. Gross. The table gives values for a function f at selected values of m. Which of the following graphs could represent these data in a semi-log plot where the vertical axes are logarithmically scaled? That's a terrible word. All right, a semi-log plot basically takes a coordinate plane and makes it look different so that when you graph something that's logarithmic, you end up with a straight line. Okay, semi-log plots, basically what it looks like is the vertical part of it is you'll have a straight line, and then it gets smaller, and then it gets smaller, and then it's like really small like that. You guys are just regular old graphs. So let's get rid of you, and let's get rid of you. If you look closely and squint your eyes, you could see this process where you have all this space and then it gets closer and stuff like that. And the same thing happens for this one right here for D as well. Here's the situation though. The goal and the purpose of a semi-log plot is for you to demonstrate a logarithmic equation as a linear equation. So if I look at where these points are, C follows these points, okay? So like here would be 1, and then like, you know, that would be, I guess that if that's 10, then that would be my 18, and then 2 would be my 30, and 3 would be my 58, which happens up here. And my dots are represented in a straight line. Looking at these numbers, you know that these numbers are not linear. This guy gives you something that's curved. Again, one last time, the goal of a semi-log plot is to represent logarithmic data as something that looks linear, and C is the guy that does that. The velocity of a particle in meters per second can be modeled by a periodic function v of t for t is greater than 0. Now, okay, so a particle, basically you have this object moving, and this is going to be the velocity. Here is your graph showing that. So you have this weird periodic function, which means it repeats every now and then. A portion of the graph is shown below. Including units, what is the average rate of change of the velocity from t equals 1 to t equals 21? 9 plus 10. So let me see here. These go by normal numbers. So when t is 1, I have what appears to be, oh, this doesn't go by numbers, normal numbers. That's 1. So t of 1 is 1. Terrific. Let's find 21. It's not there. So when you have a periodic function, here's a little trick. I don't want to continue this graph because I'm not a good artist and I don't want to try to draw the grid. That's no good. It looks like what happens is this repeats every 1, 2, 3, 4, 5, 6 spaces, right? We start out by going one flat line, then down, then up, then down, then 2 flat lines. So every 6 spaces, it repeats. In order for you to find out what's going to happen at 21, what you do is you take 6 and you divide that from 21 and find out your remainder. So 6 divided by 21 is 3. 3 times 6 is 18. Your remainder is going to be 3. So t of 21 has the same behavior as t of 3. And at 3, 1, 2, 3, you get 2. Okay, so now we need to set this up. We are being asked to find the average rate of change. The average rate of change is given to us by the formula f of b minus f of a over b minus a. Well, in this case, I don't have f's, I have t's, and I do have f's. I have v's, I believe. There you are. So it's going to be v of 21 minus v of 1 over 21 minus 1. V of 21 we already said is 2. V of 1 we already said is 1 over 21 minus 1 is 20. So to put it all together, because they want us to include the units, we have 2 minus 1, let me get my calculator, is 1. We have over 20. And this is the average rate of change, which is something per second, meters per second. So meters per second. Now, some of you might be thinking, you treated t of 21 like t of 3. That's correct. But it still is 21. So we're not going to do 3 minus 1 down here. Very, very, very tricky. We still have to pretend that we're extending all of this time over here. But, you know, that's what we get. 1/20th meters per second. Not very fast this particle is going at that amount of time. But it's average rate of change, not total distance traveled or total, rate. So kind of a bizarre problem. A line is drawn from 0, 0 to the point shown to create an angle A with the positive x-axis. All right, so here's the positive x-axis. I'm going to try to draw a line from there to there, and I had it, and then I blew it, but if I just, make it a nice thick outline, you'll never know that I screwed it up so badly. Okay, so there's my line. Boom. It's called angle A. Boom. Write a ratio for sine A, cos A, and tangent A. Basically what we're looking at is we're looking at some geometry SOHCAHTOA stuff, but we're trying to get rid of the concept of SOHCAHTOA. SOHCAHTOA, of course, gives you those trig ratios with opposites and adjacents and hypotenuses, if that's even a word, yada, yada, yada. But let's not memorize that for pre-calc. Now that we're in AP Precalculus, let's try to memorize these instead. Sine of theta, or in this case A, is going to be my y value over my radius. Okay. Sine of, let me get a different color, sine, or rather cosine of A is going to be my x value over my radius, and tangent of A is going to be my y over x. Now, where are these y's and x's coming from? Well, if I were to look at just sine and think of SOHCAHTOA thoughts, SO stands for opposite over hypotenuse. My opposite side is basically how high I go to hit my y value. My hypotenuse is how long my radius is. So this is what I want to memorize for AP Precalculus. Get rid of SOHCAHTOA. All that stuff that your geometry teacher back in the day, ignore it. It's gone. It's dead. Now, what do I know? I know my x value is 1.95. I know my y value is 2.9. Is my r 1? No. My r appears to be 3.5. My r appears to be 3.5. So sine A in this case is going to be my y value, 2.9, over my radius, 3.5, and we'll leave it like that. Cos A is going to be my x value, which is 1.95, over my radius value, which is 3.5. And tangent is going to be my y value, which is 2.9, over my x value, which is 1.95. So you will see this a lot. I'm going to make a lot of videos that look very, very, very similar to this. Watch and like them all. Please, I beg you. Please, I need the money. All right, let's complete this unit circle. This is not the only unit circle video that I have, so I highly suggest that you watch both of them just for fun. Now, let's start out the unit circle by labeling my degrees. Now, we always deal with radians here in Precalculus land, so we always start out at the positive x value, the positive x-axis at 0 radians, and then up here you have pi over 2 because halfway through it is going to be pi, so I'll put that there, which makes you 1.5 pi, also known as 3 pi over 2, like so. Okay, this is going to be 1/3 of my way through, 1/2 of my way through, and 2/3 of my way through. So 1/3 of pi over 2 is going to be pi over 6. Half of pi over 2 is going to be pi over 4. And 2/3 of pi over 2 is going to be pi over 3, because it would be 2/6 pi, or yeah, 2 pi over 6. Okay, coming over here now, I'm going to add 1/3, so that's 2 pi over 3. This is halfway between pi over 2 and pi, so that's 3/4 of a pi. And then you're 2/3 of my way through, so you're going to be 5 pi over 6. Okay, and now this part is just a matter of you taking all of these values and adding a pi to it, or, you know, whatever over whatever. So like 6 pi over 6 plus pi, you know, plus pi over 6 is going to be 7 pi over 6. Okay, this is going to be 5 pi over 4 because you're going to add 4 over 4. This is going to be 4 pi over 3 because you're going to add 1 to that. And then this is going to end up being the same idea. You're just going to add 1 to that. So that's going to be 5 pi over 3, like that. This is going to be 1 plus that, so 7 pi over 4. And last but not least, we're going to add 1 to that, so 11 pi over 6. Okay? All right. This is a unit circle. So you are, let me get different colors now that I have all my pi's written out. You are going to be the point 1, 0. You are going to be the point 0, 1. You are going to be the point negative 1, 0. And you are going to be the point 0, negative 1. Now, the trick behind filling out the unit circle is you kind of want to imagine everything as root something over 2. Okay? Root something over 2. Now, when I work my way around, okay, you're going to start out with root 3 over 2. Root 2 over 2. And root 1 over 2. The square root of 1 is 1, so you can just do 1 over 2. Now, working my way backwards is literally working my way backwards. You are now root 3 over 2. You are root 2 over 2. and you are root 1 over 2, which is just 1 over 2. This is quadrant 1, so the points are given to you as a positive value and a positive value. Leave it like that. Now, as you keep going, this point lines up with that point over there. But I know that this is quadrant 2, which means the x values are going to be negative, but the y values remain the same. So you are 1/2, negative 1/2, let me make that more obvious, negative 1/2 root 3 over 2. You are going to be negative root 2 over 2, regular root 2 over 2. You are going to be negative root 3 over 2, 1/2. Okay? As I come down here to quadrant 3, you guys seem to line up very, 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 very nicely. However, this is quadrant 3, which means everything is negative, 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 negative. Okay, and you're just going to follow the same procedure as I do over here. So you are negative root 3 over 2, 1/2, root 2 over 2, root 2 over 2, both negatives, and you're going to be the same as that, negative 1/2 and negative root 3 over 2. Last but not least, we're going to continue the process. This is quadrant 4, which means you're going to have a positive value and then a negative y, positive value, then a negative y, positive value, and then a negative y. And these guys seem to line up nicely. So I'll call you positive 1/2, negative root 3 over 2. I'll call you positive root 2 over 2, negative root 2 over 2. And I'll call you positive root 3 over 2, negative 1/2. Okay? So basically, I mean, I don't know. It is what it is. Unit circle is never the prettiest thing in the world, but once you kind of figure out the starting point, the rest of it just falls into place nicely. So you don't have to go crazy trying to memorize too much. But there it is, unit circle. All right, we have a really strange one here that seems like it should be easy, but it's not. So let's take a look at it. An angle measuring 2 pi over 3 radians is in standard position and intersects the unit circle at point S. Okay, so we're talking unit circle thoughts. So I'm going to draw a unit circle, not super necessary because of how strange this problem is. Look, it's absolutely perfect. No flaws here whatsoever. It gives us sine of our angle equals negative 1/2, and it also gives us cosine of our angle equals root 3 over 2. What is the y coordinate of point S? Now, when we're dealing with unit circle, unit circle, unit circle, unit circle, we can use the fact that our x value is cos theta, our y value is sine theta, right? It wants the y coordinate of this point, which means it wants this guy right here. And it tells us what this guy is. It tells us that it's negative 1/2, which, just for funsies, would also mean that the x value is root 3 over 2. So this is our answer. We're done. But I want to kind of analyze this because I did this problem, I looked at it, and I approached it the wrong way. And then, of course, I deleted it. And you're never going to see that because, no man here makes mistakes, even though I do it all the time. My commenters remind me. This point lives right here. And you're like, hold on, time out. Wait a minute. If the angle measures 2 pi over 3 radians, this is pi. 2 pi over 3 is less than pi. Shouldn't our point be up here? Yes, if you're going in the positive way. When you're dealing with an angle in standard position, angles in standard positions always start out with the positive x-axis. However, it's allowed to go this way if they don't tell you that that's the way it's going. So kind of a tricky problem. Not a big fan of it because initially when I did this, I went this way and I figured out that my dot should be up here, but it doesn't say that it's it has to go in the positive direction. So it tricked me, and I don't like being tricked. I don't like being fooled. Determine the general expression for the input value of all points of inflection of the graph g of theta equals cos theta. If you don't remember what a point of inflection is, or an inflection point is, wherever your graph changes concavity is when you have an inflection point. Okay, so let's graph cosine. Let's graph cosine. Cosine starts up here at 1, bottoms out at -1. It starts up here, hits the x-axis at pi over 2, bottoms out, comes back up to pi, comes back up and hits at pi over, or 3 pi over 2, and then repeats the process at 2 pi. So, so the input value for all the points of inflection are basically where we see this change in concavity, like here, here. So like 1, or half a pi. Well, that was a close one. So half a pi, 3/2 pi. Basically, every half a pi plus 1. So let's set it up like this. Y equals half a pi plus 1k, where k is any integer. Okay, that's going to be the input value. Half a pi plus 0 is going to be half a pi. Boom. Half a pi plus 1 is going to be 3 pi over 2. Boom. And then so on and so forth. So this will give us like a nice little equation to give us the points of inflection for any inflection point. Crazy problem, but, you know, we did it. All right. We are being asked to find the sine and the cosine function of this graph right here. Now, this is a sinusoidal function, and it's not at all what it should look like if we know what sine and cosine looks like. So let's do the sine first and hope that when I do the cosine part, a lot of things repeat. Here's a hint, it will. This is what I know sine looks like. Okay, this is what I know sine looks like. I know sine starts at 0, 0. It peaks out at 1, it bottoms out at -1, and it repeats itself every 2 pi. So peaks out at 1, bottoms out at -1, and repeats at 2 pi. We don't have that. We don't have that at all. So what I'm going to do is I'm going to look at this picture and try to figure out where the starting point would be and go from there. So if I were to start halfway in between the top and the bottom, where it starts to curve up, where it starts to be concave down, it looks like a good starting point would be right there. So now what I'm also going to do is write out the general forms for a sinusoidal function when using sine. Okay, that form is y equals a times sine, where I'm multiplying inside b times x minus c, close it, plus d. A is the amplitude, okay? Pretty easy to find, generally speaking. B is the frequency. I'm going to have to do a little bit of math. C is going to be a phase shift, which means horizontal, which means left and right. Keep in mind, whenever you're dealing with stuff inside the x part of the parentheses, everything is backwards. And then you have plus d. And d is going to be a vertical shift, just like it seems to always be whenever we deal with adding stuff outside the parentheses. So let's see what we have first. Let's start out with the amplitude, because that's usually the easiest to find. The amplitude is found by doing the very maximum and the very minimum, so A, Now taking that maximum number, which is 2, minus the minimum number, which is 0, subtracting that and dividing it by 2. The amplitude is not the top minus the bottom, and it's the size of the whole thing. It's half of the whole thing. So that's where we kind of get this average-looking formula from. 2 minus 0 is 2. 2 over 2 is 1. So the amplitude is 1, which means life is easy. I don't have to write that really difficult number. B is found by doing the frequency, which in order to do the frequency, I need the period. Now, the period is where this wave process repeats. So what we need to do is we need to find an obvious spot where this repeats. So it looks like the very top of the wave and the very top of the wave happen here. So the period can be found, that's not how you spell period. The period can be found by doing this right side here, which is 5 pi over 2 minus the left side minus 7 pi over 2. So we have a double negative, make it positive. 5 pi plus 7 pi is 12 pi. 12 pi over 2 is 6 pi. Now, does that mean B is 6 pi? No, no, no. You find B by taking 2 pi and dividing your period. 2 pi divided by 6 pi's, pi's cancel out, B is a third. Okay? There you have it. Now, what I have here is my starting point is now this guy right here. That's kind of like my new origin. How do I get to that new origin? Well, I have a positive phase shift. I'm moving to the right what appears to be pi. So when you move to the right what appears to be pi, what you're actually doing is you're doing x minus pi. Remember, when you move to the right, it's the opposite of what it appears to be. So my parentheses is going to be x minus pi. The way that you find D is found by doing the midline, which I kind of already created, but let me write it out a little bit further. The midline is the horizontal line that cuts my wave in complete halves. Wherever that goes through, whatever y value that horizontal line is going to be your midline, which is going to be your D. So in this case, D is 1. Now I have enough information to put all of my sine stuff together. Y is going to equal an amplitude of 1, which is invisible 1, don't need it, sine. My B is a third, parentheses, x minus pi, because it's right 3, close it, and my D is positive 1 because I shifted up 1. That's my sine. Now I need to find my cosine. And if you're like, oh no, I have to start over. Nope, because with the cosine, the amplitude will be the same, the midline will be the same, and the period and the frequency will be the same. So the only thing that changes is this guy right here. So let's kind of get rid of you. You're now dead to me. I don't need this picture anymore. And I'm going to rewrite this equation and sneak the word cosine in there if I can make it look pretty enough, and I just did. So cosine. All right? What does cosine look like? Well, cosine starts up here at 1, goes through half a pi, bottoms out at -1 at pi, and then repeats itself at 2 pi. Okay, repeats itself at 2 pi. So where can I find a peak to start at? How about here? That is a peak that I can start at. Okay, so how can I get to that guy there? Well, I can get there by going right 5 pi over 2. Now, if you're confused and if you're wondering, well, couldn't I use that guy right there? I sure could. The nice thing about periodic functions is they repeat themselves, and so it doesn't really matter which peak that I choose, so I'm choosing this one right here, 5 pi over 2. So 5 pi over 2 is the only difference that this is going to be. So everything else is going to stay exactly the same, but since I'm phase shifting right positive 5 pi over 2, that is going to be x minus 5 pi over 2. These guys stay exactly the same. Exactly the same, except for this guy, and now I'm calling it cos. So y equals the amplitude of 1, so invisible 1, cosine, my frequency didn't change because my period didn't change, x minus 5 pi over 2, that's the only thing that did change. My midline didn't change, so it's still plus 1. Then there you have it, sine and cosine functions. You can't spell functions without fun, and that's what this was. So like and subscribe. Use a regression to determine a sinusoidal model for the data set above. Identify the amplitude of the model rounded to the nearest tenth. So what we're going to do is we're going to go off to a calculator. We're going to type this in, do sine reg, and come up with an equation. Once we have an equation, we'll be able to identify the amplitude of that equation just by looking at the function that we're given. All right, boys and girls, let's do sine reg. Start out by going to stat and then hit edit. We're going to type in our x values, 10, 12, 14, okay, 12, 14, 16, 18, and 20. And then you type in your y values, which is 28, 15.6, 20.4, 35.6, 40.4, and 28 again. The way you do sine reg is you go to stat, you go to calc, all the way down here to C, I believe, is sine reg. Look at it, sine reg. Okay, iterations, don't worry about this. I won't need to use this function later. My period looks like it happens between 28 and 28. My period's 10. So I just figured that out. And I should be able to calculate. And we get the equation y equals 13.007 sine 0.628x minus 3.1388, so 139, close the parentheses, plus 28. So let's go back and write that out and answer the question that they're asking us. All right, so don't ever expect sine reg to be pretty. It never is. But we came up with an equation, and that equation was y equals 13.007 times sine of 0.628x minus 3.139, close it, plus 28. The question here is, it asks us to find the model, so we wrote it out. Identify the amplitude. Well, the amplitude is the number attached to sine at the very beginning. So my amplitude is at 13.007. Okay? So there you have it. A sinusoidal regression. I love it so very much. Like and subscribe. Use the definition of tangent to explain why y equals tan x has vertical asymptotes at x equals 2k, basketball, minus 1 pi all over 2 for any integer k. Well, what is the definition of tangent? Well, tangent x is the same as sine x over cos x. Now, vertical asymptotes exists when the denominator is equal to 0 as long as the numerator is not equal to 0. So we have to take a look at both of these. So let's take a look at both of these. Let's label sine in red, and let's graph what sine looks like generally speaking. Okay? Keep this very simple. Sine starts right here, peaks out at 1, bottoms out at -1. It comes up here at half a pi, and then hits the x-axis at pi, comes back down, hits the x-axis at 2 pi, goes back up, hits the x-axis at 3 pi, and looks something like this. Now, why is this important? because x is 0 at 0, and pi, and 2 pi, and 3 pi, and stuff like that. That's for sine. Now, if you're like, if we only care about cos x, why are we doing sine? I don't know, just in case there's holes or anything like that. There won't be, but I had fun doing this anyway. Let's do cosine in green, my favorite color. And so let's quick graph what cosine looks like and see where we cross the x-axis there. Cosine starts at 1, bottoms out at -1. So if it starts at 1 and bottoms out at -1, it crosses the x-axis at pi over 2. Then it bottoms out at pi and crosses the x-axis at 3 pi over 2. Then peaks out at 2 pi and then hits the x-axis again at 5 pi over 2, and so on and so forth. Okay, so my zeros here are pi over 2, 3 pi over 2. Since this is periodic and it's going to keep this process, you will notice that there's no overlap between these numbers and these numbers. So cosine hits the x-axis, or in other words, is 0 at stuff like pi over 2, 3 pi over 2, 5 pi over 2. Well, how do I write that out as a general equation? Well, we would say something like pi over 2. And if I needed to, include like, 3 pi over 2 and 5 pi over 2, basically I want to multiply this guy by every single other number, every odd number. How do I write out an every odd number? 2k minus 1 gives me every odd number. So again, if I were to plug in like 1, I would get 2 times 1. 1 minus 1 is 1. So 1 pi over 2, like you. And if I were to plug in 2, then I would get 2 times 2 is 4. 4 minus 1 is 3. 3 pi over 2, so on and so forth. That, when simplified, and that when multiplied to the very top, gives you x equals 2k minus 1 pi all over 2. And so since vertical asymptotes occur when the x values of the denominator equal 0, as long as it doesn't do the same thing for the numerator, these guys are the equation, or is the general equation for the vertical asymptotes of tangent, as long as it's just regular tangent. When it's not regular tangent, it complicates things. But that is how we use the definition of tangent to come up with the vertical asymptotes in that form right there. Fun! Given f of x equals 1/3 sine x on x being between pi over 2 and negative pi over 2, find its inverse, and then sketch the inverse, and then state the domain and range. Well, this is going to be great. Well, all right, let's find the inverse. So whenever I find the inverse, I like to pretend that f of x is y, and so that's going to equal 1/3 sine x, right? Step number 1 when finding the inverse is swap the x and the y, so 1/3 sine y. Okay, multiply both sides by 3, and that will allow the 1/3 attached to the sine to go away. Okay, so you are gone, and now we have 3x equals sine y. And if you're like, whoa, buddy, whoa, that's a lot of space for you to leave right there. I know, because the next step is to get rid of sine. And the way you're going to get rid of sine is you're going to inverse sine both sides, like that. So you inverse sine both sides. That crosses out. Okay, that gives us y equals, I'm just, flipping sides, inverse sine of 3x. So inverse sine of 3x. And then I need to write it out as f inverse of x equals the inverse sine of 3x. Now I'm going to sketch this from the point of view of f. Okay, I'm not going to act as if I have the inverse sine memorized. I kind of do, but I don't really. So let's kind of remember what sine, 1/3 sine of x looks like really quickly. Okay, really quickly. This is f of x. Okay, this peaks out at 1/3, bottoms out at -1/3. okay, starts at 0, 0. It goes up and hits that 1/3 at half a pi, which so happens to be the end of my domain, which means it goes down here. Let's get rid of that. Let's try that again. It's going to go down here and bottom out, okay, at negative half a pi. So a little more curve, and a little more curve. There we go. All right, that's okay. Now, when I look at this from a table point of view, okay, that's my graph. We know that an inverse is going to be the reflection of the y equals x, but let's look at it this way also. Let's look at it from a table point of view. Here's going to be my x and f of x. My key points are at negative pi over 2, I'm at negative 1/3. At 0, I'm at 0. And at positive pi over 2, I'm at positive 1/3. Now, the table of an inverse is flipped. So its inverse is going to be negative 1/3, negative pi over 2. Flip them. 0 flipped with 0 is 0, 0. And 1/3 is going to be my x value, and pi over 2 is going to be my y value. So now when I graph this, okay, when I graph this, I'm going to peak out at pi over 2, and I'm going to bottom out at negative pi over 2 down here. I'm going to go to the right 1/3 and to the left negative 1/3. And when I graph this, I have that 0, 0. I have that dot right there poorly drawn, and that dot right there poorly drawn. And this is going to be the action we come up with. Okay, so that is the graph of its inverse. Similar, very similar, but if you can kind of see, if I were to draw like a perfect diagonal there, this would kind of flip and that would kind of flip, and then that's kind of what's happening there. All right, now what does that do with the domain and the range? Well, here was the domain of my original problem, which means my range is going to be the domain of my original problem. Now, when I graphed my original problem, let me just write that out. Let me just write it out. When I graphed my original problem, it peaked out at 1/3 and bottomed out at negative 1/3. Okay, it peaked out at 1/3. So my range for regular f of x was negative 1/3 to regular 1/3, which means my domain of the inverse is going to be the range of the original. Like that. Okay, so I approached this problem slightly differently, where instead of trying to memorize what the inverse looks like, I found the inverse and then graphed the inverse using information about the original. Well, wasn't that fun? It was. Find all the solutions for negative 15 plus root 3 all over 3 equals negative 5 plus tangent theta plus 3 pi over 4. Ugh. First things first, let's get rid of that 5, that negative 5, and we'll do so by adding 5 to both sides. Now, if I'm going to add 5 to something over 3, I'm going to turn this into 15 over 3 because that's what 5 is when I multiply the top and the bottom by 3. That allows these guys to cancel out, and you're left with root 3 over 3 equals tangent theta plus 3 pi over 4. Now, how do I get rid of that tangent so I can open up that whole parentheses there? Inverse tangent, of course. So I'm going to inverse tangent root 3 over 3. That allows that to cross out. Now, here's the thing that I have to be careful of. I am asking you what angle gives me root 3 over 3 if I take the tangent of it. So where is tangent going to give me a positive slope? Well, tangent is going to give me a positive slope because remember, tangent gives me slope of a ray. When x over y is positive, or y over x is positive, and y over x is negative and negative, which makes you positive. So quadrant 3 seems to do it. Okay, now the tangent, the inverse tangent of root 3 over 3 in the positive axis is going to be root pi, or regular pi over 6. But also, and this is my and, not plus, also in the third quadrant, it's going to be 7 pi over 6. And that's going to equal theta plus 3 pi over 4. Now, you might be thinking, I think he's doing a bit too much. And you're kind of right. You're kind of right. But let's just do it anyway. We now have two equations that we have to solve for. We have pi over 6 equals theta plus 3 pi over 4. And we have 7 pi over 6 equals theta plus 3 pi over 4. Okay, this is a learning process. This is not me just kind of, let's just blindly do the problem. Let me do the problem, realize that I did too much, and we'll explain the mistake in a minute. Let's subtract 3 pi over 4. So that would basically be like 2 pi over 12 minus 9 pi over 4. So negative 7 pi over 12 is going to equal theta. And if I do the same thing over here, minus 3 pi over 4 minus 3 pi over 4, that would basically be like me saying, what, 14 pi over 12 minus 9 pi over 2. So 5 pi over 12. That's going to equal theta. Here's the thing with tangent. And this is where I'm now going to realize, I did too much. The period of tangent isn't 2 pi like it is for sine and cosine. It's regular pi. What's negative 7 pi over 12 plus pi? You guys are the same exact thing. I did too much, which means the main guy that I care about is either one of these. Now, hold on, time out. I have no interval. I have no interval whatsoever. So what I need to say at the very end here is theta is going to be like negative 7 pi over 12, or 5 pi over 12, or plus another pi, or plus another pi. So I'll pick one of these, 5 pi over 12 plus k pi. What this does is if I let k be any integer, if I said k is 0, then I get 5 pi over 12. If I said k is negative 1, then that means minus pi, which is negative 7 pi over 12. Or if I add 2 pi, or if I add 8 pi, any of these guys will work. So kind of tricky, kind of weird, lots of fun. Graph f of x equals 2 cosecant pi x. All right, this is how I graph my reciprocal functions. I kind of view this from a standpoint that this is basically the same as 2. 1 over sine pi x, right? And so what I need to do is I need to graph this guy and let this guy be my guide. Now, what do we know about this? Well, amplitude is 2, so that helps. Okay, amplitude is 2. And also, there is a pi in front of x, which means my frequency is pi. And for sine functions, if your frequency is whatever, you find your period by doing 2 pi over that whatever. And my whatever is pi, so cross out the pi's, and my period is 2. So what I'm going to do is I'm going to draw, this is a very rough sketch, so, don't cling on accuracy, especially since I can't draw lines with this thing. My period is 2, so not pi's, which is why I didn't get some kind of trig graph. So I'll go 1, 2, 3, 4. I'll go 1, 2, 3, 4. Okay. Now drawing out, you know what? I also need these. These will help. 1, 2, 3, 1, 2, 3. All right. So drawing out my rough draft of what this looks like. Okay, I have an amplitude of 2. I have a sine whose period is 2. So I start here. Everything repeats. Everything repeats. So I go up to 2, come back down, go down to negative 2, come back up. Go up to 2, come back down, go down to negative 2, come back up, and vice versa. So go down to negative 2, up to regular 2, negative 2, regular 2, boom. Okay, so this is like my rough sketch. Now, while I'm drawing this out, this is going to be my guide for what this cosecant function is going to look like. Anytime my graph goes through, my sine graph, my rough graph, goes through the x-axis, that means it hits 0 in the denominator for a cosecant. And when 0 is in the denominator for your cosecant, well, that, boys and girls, is a vertical asymptote. Vertical asymptote, vertical asymptote. So as I draw all these vertical asymptotes, including you, okay, the next thing that I'm going to consider is the fact that this is a cosecant function which looks like alternating parabolas. Okay, cosecant functions look like this. Usually it starts at 1 and -1, but since the amplitude is 2, these guys are going to start at 2 and -2. So my final graph is going to look something like this. Okay, alternating parabolas looking things. Okay. So again, you know, I'm not going to win any awards for the prettiest picture ever, but I allowed the sign, which is in green, to be my guide, which gave me vertical asymptotes, which gave me the final graph at the end of the day. So not the prettiest, but I did it. Buckle up for this one. It's a doozy. Find the exact value of tangent 5 pi over 12. Obviously, we're not given on the unit circle 5 pi over 12, so I need to kind of rewrite this in a way where I use some of those numbers that seem to appear on a tangent circle, and I can either add or subtract them. Now, what I'm going to do is I can get to 5 pi by doing 2 pi and 3 pi over 12. Now, what that does is once I have those officially split up, I can write this out as tangent. 2 pi over 12 is pi over 6, so a unit circle number, plus 3 pi over 12 is pi over 4, another unit circle number. Now, you may have the sine, and hopefully you do, and the cosine addition properties memorized, but you probably don't have the tangent. So I'm going to go about this in probably the longest way possible, just in case you don't have tangent memorized. Tangent is the same as sine over cosine. So I can write this out as sine pi over 6 plus pi over 4 all over cosine pi over 6 plus pi over 4. Okay? And then I deal with each one individually, which is not going to be super pleasant. But you know what? That's kind of what I get for not having tangent memorized, because honestly, I don't have it memorized. So basically, when you add two sines, what you do is you do sine of the first, cos of the second, plus cos of the first, sine of the second. So sine of the first, cos of the second, plus cos of the first, sine of the second. Barely squeezed that in there. Barely squeezed it in. Cosine is, if you're adding them, is going to be cos cos minus sine sine. So cos of the first, so cos of pi over 6, cos of the second, so pi over 4, again, minus sine of the first, so sine pi over 6, sine of the second, pi over 4. Now, I'm assuming at this stage we feel okay with the unit circle, so I'm not going to spend a lot of time reminding ourselves how to find the sine of pi over 6. So, you know, we're just going to go right to it. Sine of pi over 6 is a half. Cosine of pi over 4 is root 2 over 2. Plus cosine of pi over 6 is root 3 over 2. And sine of pi over 4 is root 2 over 2. Cosine of pi over 6, which I already did, is root 3 over 2. Cosine of pi over 4, which I already did, is right here, root 2 over 2. Minus sine of pi over 6, which I did over here, is a half. Sine of pi over 4, which I did, is root 2 over 2. Okay, so this is where it's going to get fun. Root 2 times 1 is root 2. 2 times 2 is 4. Root 3 times root 2 is 6. 2 times 2 is 4. You're adding on top. All over. You're subtracting on the bottom. Let's get a different color, all these colors. Root 3 times root 2 is root 6. 2 times 2 is 4. And purple. 1 times root 2 is root 2. 2 times 2 is 4. So they combine nicely. Root 2 over 4 plus root 6 over 4 is root 2 plus root 6 over 4. Root 6 minus root 2 over 4. Now, since these are both over 4, I can multiply the top and the bottom by the reciprocal of the denominator, which I'm just going to kind of skip that step and go right to, actually, you know what, let me write it down here because I know what's going to happen next. Root 2 plus root 6 over root 6 minus root 2. Now, chances are you're going to have a teacher or a test or a problem where you're not allowed to have square roots on the bottom. So how do I eliminate a root minus a root? You do the conjugate, which is going to be multiplying the top and the bottom by that root plus the root. And what that does is that gives us difference of squares type problems. Now, upstairs, it doesn't give us difference of squares. It just, foils out. So if you were to put these in parentheses and put these in parentheses, you would FOIL things out. Root 2 times root 6 is root 12. I can simplify that. Root 2 times root 2 is 2. Root 6 times root 6 is 6. And root 6 times root 2 is root 12 again. Root 6 times root 6 is 6. Plus root 12 minus root 12. So the root 12s go away. Root 2 times root 2 is 2, so that's going to be minus 2. All right, so that's 2 root 12. If I add the 2 root 12s together, plus 8. 6 minus 2 is 4. Still not done yet. Root 12 can be simplified to 2 root 3. So this becomes 4 root 3 plus 8 over 4. Now, still not done, because I have a 4, an 8, and a 4. They're all divisible by 4. So last but not least, 4 root 3 divided by 3 or 4 is regular root 3, and 8 divided by 4 is 2. That is my final answer. So I told you, buckle up. Okay, hopefully you did. It's the law in many states, unless you're sitting in the back. All right, never mind. Like and subscribe. Graph the polar coordinate -3, 23 pi over 12. Now, when you graph a polar coordinate, this is not the same as what we're used to, the rectangular coordinate. This is not telling us, let's go left 3 and then go up whatever the heck that number is. This first number is the magnitude. This is how long or how far away we're going to draw our dot from 0, 0, also known as the pole. This second number is the degree that we spin counterclockwise from the positive x-axis. Okay, like we've always done. Now, 23 pi over 12 is not visible, but it would be right here. Okay, it's literally that last spot before we hit 2 pi. Now, that's great and all. So I spin this around, I see 23 pi over 12, and I'm like, well, wait a minute. My magnitude is -3. That means I'm not going to go 1, 2, 3 towards 23 pi over 12. I'm going to go in the opposite direction. So 23 pi over 12 is this line, which in the opposite direction, spinning it around, is going to be this line. And I would go 1, 2, 3 spaces down this line, which represents 11 pi over 12. So the way you can view this is if you're going to have a negative magnitude, just add or subtract 1 pi to this number here and make that negative magnitude positive, and you get the same thing. So negative 3, 23 pi over 12, is the same as positive 3, 11 pi over 12, because 23 pi over 12 minus pi is that number right there. So there you have it. That's how you graph a negative magnitude polar coordinate. Fun, 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 fun. Write a polar equation using the graph below. This is what I'm looking at. And what this looks like is a rose. Now, I did a video a couple problems ago where I had a rose. And the equation looks something like r equals some amplitude cos some number times theta. What we learned is when I had an odd number in front of theta, I had that many petals. I have 1, 2, 3, 4, 5, 6, 7, 8 petals. This is an even number. So when I had an even number, I had 2 times that many petals. This has 8 petals. So if I were to take a number and multiply it to 2 to get 8, that means my n would be 4. So this is going to be 4 theta. Okay. Now, fun fact here. I said cosine. Sine is also an option. If you're wondering, is this sine or is this cosine, and how do I figure it out? Well, if this was a cosine, cosine would always start out on the x-axis. This doesn't start out on the x-axis. This starts somewhere up here, which means this isn't cosine. This is sine. Tricky, 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 tricky. Now, I have to find the amplitude. That's the easy part. The amplitude is the maximum value that these petals stretch out to. These all stretch out to 3, which means the number in front of sine is also going to be 3. So the equation for this polar graph here is going to be r equals 3 sine 4 theta. Isn't that nice? Find the average rate of change of the polar equation r of theta equals 2 cos 4 theta plus 1 on this interval pi over 8 to pi over 2. All right, so we know that the average rate of change is going to look like this. R of b minus r of a over b minus a. We know this from Unit 1. That would be my a. That would be my b. So what I need to do is I need to find r of pi over 2 and then find r of pi over 8. R of pi over 2 is going to be 2 cos 4 times pi over 2. Simplify that in a minute, plus 1. 2 cos 4 times pi over 2 is going to be 2 pi. So 2 cos 2 pi plus 1. The cosine of 2 pi is 1. So 2 times 1 plus 1 is 3. So this guy is going to end up being the number 3, no big deal. To find r of a, I'm going to do r of pi over 8. So the same idea, 2 times cosine 4 times pi over 8, close it, plus 1. That becomes 2 times cosine. 4 over 8 is a half, so a pi times a half is pi over 2. Pi over 2 plus 1. Cosine of pi over 2 is 0. So that's nice. So this becomes 0 plus 1, which is 1. So now I have r of b, which is 3, minus r of pi over 8, which is 1, over b minus a, which is going to be, that's going to be the gross part, pi over 2 minus pi over 8. So that's going to be the worst part. 3 minus 2, not so bad. I'll turn u into 4 pi over 8 so I can subtract these two fractions. So 2 over 3 pi over 8. Let's multiply the top and the bottom by 8 over 3 pi. multiply the top and the bottom by 8 over 3 pi. And at the end of the day, I end up with 16 over 3 pi. That's my guy. Fun stuff.